Namaskara. We will continue with some more problems on the DC circuits. In that respect, consider this problem. Two power sources supply a load of 10 ohm. Find the voltage across 10 ohm. The circuit given is this. This has been given as 120 volt, 5 ohm, this is 10 ohm and this is 1 ohm, this is 110 volt. It is required to find the voltage across 10 ohm. If I connect a voltmeter here, it records the voltage across this 10 ohm, which is nothing but the drop in this 10 ohm. In that respect, if I call this one as say A and B, the voltage VAB will be equal to the current flowing through that's IAB into the resistance 10 ohm. What's the current flowing through this 10 ohm? In that respect, the same circuit can be redrawn like this also. This way. This is 5 ohm, 1 ohm, 10 ohm, this is 110 volts, this is 120 volt. If I assume a current of say I1 in this loop and this as I2, this being A and B, IAB is obviously equal to I1 minus I2. If it is positive, the current will be in the direction of I1. If it is negative, it will be in the direction of I2. Write the Kirchhoff voltage law, apply Kirchhoff voltage law here. In that case, if I call this one as say EF, maybe it's a repetition. However, it gives us an idea how to calculate the voltage across this. In that respect, this is minus plus to minus 120 minus 5I1 minus 10I1 plus 10I2 equal to 0. This is one equation. The other equation is from this loop. If I start from A, it will be minus 1I2 plus to minus, it is minus 110 volt. Then from here to here there is no drop. As I go this way, it is minus 10I2 plus 10I1 as I am going against this current. Solve these two equations, in which case what you get is nothing but I1 will be minus 37.23 ampere and I2 is equal to minus 43.85 amperes. Once I get this one, what will be the value of current through AB? IAB will be equal to, this is I1 minus 37.23, then minus of minus 43.85 comes to 6.62 amperes. Therefore, VAB is equal to 6.62 into 10, that comes to 66.2 volt. So that's the answer. The next problem. In the circuit shown, what is the voltage across AB if A switch S is open and B switch S is closed? The circuit given is this. Ohm, 10 ohm, this is plus minus 120 . What's the voltage across AB? Now there are two cases when S is open and S is closed. When S is open, the presence of this can be ignored because no current flows through this, in which case the circuit that results into will be this. This is 120 volt, 2 ohm, 10 ohm, 12 ohm, 20 volts, and this is 100 volts. This being A and B. Again, VAB will be equal to the current through 10 ohm resistor, that's nothing but IAB. You can call this one as IAB into 10. If I assume two loop currents I1 and I2, then IAB will be equal to I1 minus I2. To know IAB and to know VAB, I have to find out I1 and I2, in which case go for the same Kirchhoff law voltage equation. For this loop, it is plus 120 minus 2I1 minus 10I1 plus 10I2 equal to 0. This is minus to plus, plus to minus, plus to minus. When it comes to this, minus to plus. That way, so sorry, this is plus to minus. Thereby, I am going against that one. Minus to plus means it is nothing but plus. This is the first equation. Going for the second equation, that is this one. If I start from here, it is minus 12I2 plus to minus minus 20, again plus to minus minus 100. As I go in the direction of I2, it is minus 10I2 and plus 10I1 will give the value, second equation. When you solve these two equations, you will get I1 is equal to and I2 is equal to 3.96 and minus 7.25 amperes. Obviously, IAB will be equal to, this is 3.96 minus of I2 is nothing but minus 7.25 comes to 11.21 amperes. This is 11.21 amperes. Therefore, VAB will be equal to 11.21 into 10 comes to 112.1 volt. That's the answer. With that, when the switch is closed, what happens? When the switch S is closed, that is this way, as such, the resistance offered by the switch is 0. Therefore, if this is nothing but the connecting wires, which is also assumed to be 0, therefore, the voltage across the switch is 0. If at all, if I call this one as say points X and Y, with that, what happens? The points X and Y will be at same potential. When they are at same potential, Y can be transferred to X, which is same as A. In which case, the presence of 12 ohm resistor along with 20 volt can also be totally ignored from the circuit. Will there be any current in 12 ohm? Yes. As such, this 20 volt battery will drive a current in this circuit, in this closed loop. The current is such that the drop in this is same as the voltage here now. With that, the resultant voltage from here to here becomes 0. Once we conclude that the resistance offered by the switch is 0 and the points X and Y are Y, X and E are at same potential, this can be ignored, and at the same time no current from this 100 volts. If it is driving any current, when it comes here, it will not flow through this, it will take this path only. Similarly, any current that's coming out from this side will not flow through this, it will only flow through this, causing a drop of 0 volt. So with that, this can be totally ignored. Now the circuit results into this. Now this will be, the resulting circuit will be this, and here it will be 110 volt, 100 volt. As such, there is no need to go for any calculation, because this voltage is across this point. As such, this point is same as this point is same as this point. That means the voltage across AB is nothing but 100 volt. However, it can be proved also by considering two loop currents I1 and I2. Here, if you go for this loop, it is plus 120 minus 2I1 plus minus 10I1 plus 10I2 equal to 0. For this loop, it is plus 10I1 minus 10I2 plus to minus 100 equal to 0. If you simplify this, I1 comes to 10 amperes, I2 will be 0 ampere. VAB is nothing but IAB into 10 ohm. IAB is nothing but I1 minus I2, which is nothing but 10 amperes. Therefore, the voltage across is 100 volt. That. Find the power dissipated in 4 ohm resistor if VAB is equal to 25 volt in the circuit shown. Find the power dissipated in 4 ohm resistor. This is the 4 ohm resistor. This is 6 ohm, 5 ohm, 10 ohm. This is B and this is A. This is Vs. The voltage across this is given as 25 volt. VAB is nothing but 25 volts. VAB means A is at a higher potential compared to B. In this respect, how to find out the power dissipated in this 4 ohm resistor? P4 will be equal to, if I call the current here as I1 and the current here as I2, it will be I1 square into R1 or I1 square into 4. What is I1? I1 is nothing but equal to, as such you can see here, this voltage Vs is across this. This is a parallel circuit across this source. In that respect, these two are in series and across this voltage source. Therefore, Vs divided by 4 plus 6, that's nothing but equal to 10. If I know what is the voltage source or source voltage, I can find out I1. Now, in that respect, you can go for this expression, this equation or this loop. When I consider this loop, starting from here, you can go this way. It will be, as I go this way along the direction of the current, it is minus 10 I2, then this minus, this is plus VAB, and here it is plus, it is 4 into I1 must be equal to 0. This same as minus 10. I2 is nothing but equal to, this is Vs over the total, the resistance in this path, that's nothing but 10 plus 5 plus VAB is nothing but 25 volts, then plus 4 into, it is again Vs over, it is 4 plus 6 equal to 0. You simplify this, Vs works out to 96.63 volt. Once we get this one, I1 is obviously, this is 96.63 divided by, that is 10, that comes to 9.663 amperes, and P4 will be equal to 9.663 square into 4 will give you the value. That comes to 350 point. That's I have typed as 363 instead of 663. Anyhow, this gives you approximately this wattage. The power can be calculated. There's a typing error. That consider another problem. Examine whether the power supplied by the source is same as the power dissipated in the circuit shown. This is the circuit. Examine whether power supplied by the source or sources is same as the power dissipated in the circuit shown. In order to examine, I must know what's the power consumed in these resistors and also power supplied by these also. In that respect, what's the power supplied by this voltage multiplied by the current that's coming out here. Similarly, if the current is coming out here, the power supplied will be 5 into current that's coming out. Instead of the current coming out at the positive terminal, if it is entering like this way, it is not, say, supplying power, but it is consuming power, or it is getting charged. So that can be known, or that will be known only when the current, magnitude of the current in different patches are determined, or direction of the current and magnitude are determined. In that respect, consider I1 here and I2 here. The two loop equations will be minus to plus, that will be equal to plus 20 minus 2I1 minus to plus, that will be plus 5 minus 4I1. As this current is going this way, it is minus 4I2, and this way it is minus 8I1 is equal to 0. This is one of the equations. When you go for the other equation, that's nothing but this one. Here, if I start from this point, it is minus 3I2 minus to plus, that is plus 10. As I go this way along I2, this is 4I2, and then plus 4I1 plus to minus, it is minus 5 equal to 0. Solve these two equations to find out I1 and I2, in which case I1 will be equal to 2.38 amperes and I2 is equal to 2.07 ampere. So with that, what's the power consumed by the resistors and what's the power supplied by that? In that respect, the current is now, I1 is coming out of, because I1 has resulted in positive sign, both I1 and I2 are resulted in positive sign. Since I1 is coming out of the battery here, it is supplying power. So what's the power supplied by that's 20 volt battery? This will be equal to 20 into the current, that's 2.38 amperes. when it comes to the power here, now it is the current is coming out of the battery here, therefore P10 must be equal to 10 into I2. I2 is nothing but 2.07. When it comes to this one here, now the current through 5-volt battery, that is nothing but I5 will be equal to, if I take it as a I1 minus I2, this will be I1 is 2.38, I2 is now minus 2.07, therefore this is positive, that comes to 0.21 ampere. This is also, the current is coming out here, therefore it is also supplying power. Therefore, P5 will be equal to 5 into 0.21 will give you the power supply. The sum of this will be 2.07, this is 31, this is 47.6 watts, P10 is 20.7 watts, and this is 1.55 watts. Therefore, the total power is the sum of these three, that comes to 69.9 watts. So that's the power supplied. That's the power supplied. Will it be equal to the power consumed by the individual resistors? In that respect, the power consumed in this total power will be equal to, P will be equal to, here it is nothing but 2, the current flowing through this is I1, I1 is nothing but 2.38 square into 2 plus the current flowing through this is also same 2.38. You can write this one as 2.38 square into 8 plus power consumed in this one, which is nothing but the current in this resistor is nothing but 0.31. Therefore, this will be 0.31 square into the resistance of this one, that's 4, plus the power consumed in this, that's nothing but I2 square, that is 2.07 square into 3 will give a value of 69.9 watts. Since this power, the power supplied by the batteries is same as the power supplied by the resistors, you can say the conservation, energy conservation is satisfied. The power input must be equal to the power consumed. In that respect, say these two are same. Consider another problem. Determine I in the circuit shown. This is the circuit given. As you can observe here, these three are in series. They can be replaced by one resistor. Anyhow, we will come to that later. as the current comes here, what happens? Because this junction, the current divides itself. If I call this one as say, for example, A, B, C, D, E like that, we'll observe point B, C, D and E are at same potential. The current, some current divides here, let us say I call it as I1, and that goes this way because it's the lowest path. And here if a current I2 comes here, when it comes here, it will not take this path because the current always takes the least resistance path. When it comes here, it finds another path here, least resistance path, and then it comes this way and goes like this. So with that you can conclude the 4 ohm, these resistors are short circuited by this least resistance path or zero resistance path. In that respect, you will observe this point being same as this point being same as this one, this can be written as equal to this is 6 ohm, this is 12 ohm, this also 12 ohm. This point is A, this point is B. This point B is same as C, same as D, same as E, is same as the negative terminal of the supply. That's nothing but 120 volt. These two being in parallel, the total resistance will be, this can be reduced to one resistance. This is 6 ohm, this also 6 ohm, this being 120 volt. The current is obviously I is equal to 120 divided by 6 plus 6, that comes to 10 amperes. So that's the current. The same problem can also be analyzed in a slightly different way. In that respect, since these points are at same potential, you can write this one like this also. This is 6 ohm, this is 12 ohm, this point is nothing but A, this also A, and we have here this is 12 ohm, this point, this B is nothing but this, which is same as this D or C. And then when it comes to this here, this is, since this point is same as this point, this can be taken over to this point also. That means this 4 ohm can be written here, and this point being same as this point and same as negative terminal, you have like this. This is nothing but D, which is same as E. Between C and here, this point, call it as say F, we have C and F. This is nothing but F. We have one more resistance, that's nothing but 3 ohm. And you will observe here between B and F, we have 4, 7, 3, that's nothing but 14 ohm. Between B and F, this is also same point F, we have one more resistance, this is nothing but 14 ohm. This can be further written as equal to these three, all these are at same point potential, and these are also at same potential. All these three can be replaced by one resistance, and I can write this one something like this. In which case, we will observe there exists a open circuit point. No current can, as the current comes here, current divides here, and when it comes here, it cannot go this way to come back to the source. Therefore, the current just goes this way, ignoring this path. Or as this goes, these resistances go short circuited, no current flows, and no current flows here with reference to this reduced circuitry. Therefore, the current supplied by the 120 volt battery is 10 amperes. Design a voltage divider circuit for a 5 volt output from 12 volt battery of negligible resistance. The power consumed by the circuit should not be more than 240 volt. It is required to get an output voltage of 5 volts from a source of 12 volt battery. In that respect, this is the 12 volt battery. Have to have 5 volts means there should be two resistances in series. This is the voltage divider circuit. The voltage across this, obviously this is 5 volts. This being, call it as a R2 and this one as R1. 5 volts output and 5 volt here and this is 12 volt. The power consumed by the circuit should not be more than 240 milliwatt. What is that power consumed by the circuit? The power consumed by the circuit will be equal to, it is V square, if I call it as a Vs and this one as a V naught, then Vs square divided by R1 plus R2 should be less than or equal to 240 milliwatt. We will assume it as a equal to 240 milliwatt. I know this, therefore I get the value of R1 plus R2. Therefore, R1 plus R2 will be equal to, this is 12 square divided by 240 into 10 to the power of minus 3, that comes to 600 ohms. That comes to 600 ohms. So, I know R1 plus R2, but I do not know what is the R1 and R2. How to find out? In that respect, we know what is R2. This V naught is nothing but equal to the current flowing through in this circuit. That is nothing but I into the resistance R2. What is I? Is nothing but Vs over R1 plus R2 into R2. This will be equal to 12 divided by 600. Moreover, when this is 5 volts, this must obviously be 7 volts. So, this will be into R2, this will be 5. So, with that R2 will work out to 250 ohms. Once I get R2, I know R1 plus R2 is equal to 600. Therefore, R1 is obviously equal to 600 minus 250 comes to 350 ohms. It is quite simple that way. This is how the required output voltage is obtained by going for a higher voltage. Here, this is under no load condition. However, when a load is connected here, what happens? The circuit condition definitely changes. Let us see that one with reference to another example. Design a 2 resistor voltage divider circuit with the following data. Desired output voltage 6 volts, source voltage 16 volt, maximum load current 100 microamperes. The current in the voltage divider without load connected is to be less than 100 times the maximum load current. What is the actual output voltage when the load is connected and the percentage error? This is 16 volt. The output required is 6 volts. This is R2, this is R1. The maximum load current is 100 microamperes. The current that will go when it is loaded will be, this is 100 microamperes. the current in the loader voltage divider without load connected is to be less than 100 times the maximum load current. That means the current that flows here, if I call it as say I1, will be equal to 100 times this current, that is nothing but 100 microamperes, that comes to 10 milliamperes. So once I know that one, so what will be the value of R2 and R1? R2 will be equal to, this is 6 volts divided by the current, that is nothing but this, comes to 600 ohm. When 6 volts is dropped here, obviously the voltage available here must be 10 volts. With that, R1 will be equal to 10 divided by 10 into 10 to the power of minus 3, that comes to 1000 ohm. So these are the two values calculated to see that a 6 volt output is obtained. However, when it is loaded, what happens? Let us see. When it is loaded means this is connected to a resistance. The current flowing is now 10 milliamperes. Obviously, the current here must be equal to the current flowing through, the current I1 plus this. In that respect, the I1 will be, this is 10 milliampere plus 100 microamperes, and the current here will be 10 milliamps. So with that, what happens now? So what will be the drop here now? Once the current increases, the drop across this also increases, therefore the voltage drop across this reduces. What will be the reduction? That's what is the percentage error. In that respect, what will be the voltage available across this? We know it is this 1000 ohms. Therefore, the voltage across R1 will be equal to the total current here. This is 100 into 10 to the power of minus 3 plus 100 into 10 to the power of minus 6 into 1000. So that comes to 6 point this will be 10.1 volt, it works out. Obviously, V output will be equal to 16 minus 10.1 will come to 5.9 volts. Against a voltage of 6 volts, we have a voltage of only 5.9 volts. Obviously, the percentage error can be taken as equal to V required minus V actual divided by V required. So there is no rule it should be written in this way only. It can be written as equal to V required minus V actual over V actual also. So there are different ways of representing the percentage error. If you go for this, the required voltage is 6 minus V actual is 5.9 and this is 6 into 100 will give you the percentage error. That comes to 1 point something or so, 1.67%. When the design is being done, there will always be a tolerance. It will always be mentioned as the voltage should not be more than plus or minus say 2% or 3%. So with that in mind, the resistors can be, the values of resistors can be calculated, and at the same time, when the values, the calculated values are not available, in practice only standard values are available, they have to be selected. In that case, the voltage required may or may not be possible to get exactly to the required extent. So that completes the DC circuits. I will just give an introduction to magnetism and electromagnetism. I will just brief. The syllabus contains module 2 contains review of field around a conductor and coil, magnetic flux and flux density, magnetomotive force, magnetic field intensity, reluctance and permeability, definition of magnetic circuit and basic analogy between electric and magnetic circuits. Of course, these topics are not there for the examination. However, it gives an insight to the electromagnetic induction. Electromagnetic induction involves definition of electromagnetic induction, Faraday's laws, Fleming's right-hand rule, Lenz's law, statically and dynamically induced EMF, self-inductance, mutual inductance and coefficient of coupling. Energy stored in magnetic field, illustrative examples, force on current carrying conductor placed in a magnetic field, Fleming's left-hand rule, all these are there under this chapter. After completing this chapter, students should be able to define magnetic induction, state the basic laws of electromagnetism, state Lenz's law, describe how the right-hand rule for generators can be used to determine the polarity of induced voltage. Using Faraday's law, calculate the EMF across a conductor being passed through a magnetic field. Explain the principle of inductance, define mutual inductance, understand the importance of coefficient of coupling, calculate the force on a current carrying conductor placed in a magnetic field, examine the applications of electromagnetic induction and the force on the conductors also. So with that, we will go for the magnetic field. Whenever you consider a bar magnet, this is the bar magnet which will have the two poles, north and south pole. The presence of magnetic field is felt by the force exerted on another magnet or an iron piece or a charge moving in the magnetic field. Say if this has some region, for example here, if I keep another magnet here, for example, or for example here, it may not be attracted. So therefore you can say this is not in the field of magnetic field. However, when I bring it here, if this is north and this is south, obviously there will be force of repulsion. If it is south and this is north, obviously there will be force of attraction. The presence of the magnetic field is represented by the lines of force, which will be like this, a continuous line. It is this way. It is assumed the lines of force to leave the north pole and enter into the south pole here. These are nothing but the lines of force collectively called the flux. The unit of flux is Weber, denoted by capital W and small b. The field that exists here is less. That means the flux that is passing through this area is less than if I consider an area here, the flux is enormous here while flux is less here. The flux density B is nothing but flux divided by area is less here while the flux density here is more. The flux density unit is nothing but Weber per meter square. However, nowadays it is being changed or going for SI units. This is nothing but Tesla, which is denoted by capital T. So this is about the magnetic field. When it comes to electromagnet, what is that? Whenever a conductor the magnet can be, or the field produced, magnetic field may be due to a permanent magnet or it can be an electromagnet. This is permanent magnet, or it may be due to an electromagnet. What's this electromagnet? It has been found that whenever a conductor carries current, it produces the flux. What's the direction of the flux produced? Go for the hand rule, right hand rule. Hold the thumb in the direction of the current. If this is, for example, if this is taken as the conductor and this is the right, this being the right hand, hold it like this. Now the thumb gives you the direction of the current, the curling of fingers gives the direction of the flux produced. Therefore, the flux produced will be this way. If at all the current flowing through the conductor is changed, if it is this way, obviously the direction of the flux produced also changes. Now it has to be like this. So in that respect, it will be this way. I will repeat, it is this way. So what is the usual representation of the flux produced by a conductor? In that respect, you can see here, the conductor can be represented like this. This is the conductor. If this is the direction of the current and this is the I, what's the flux produced here now? It's obviously this way. The flux produced is in this way. This is phi. Every time the conductor cannot be represented by a long line like this. So in that case, some representation will be used. When seen from the observer, the conductor is represented by a circle. The current is going away. Think of an arrow which has a point. This is nothing but the point, and this is nothing but what's called as fletching, or you can say it is the feather end. The observer will look at the feather end, or the arrow is going away, therefore he will see the feather end. Feather end is indicated by a cross. With that in mind, what's the direction of the flux produced? You can go for either right hand screw rule or go for right hand rule itself. Hold the thumb in the direction of the current. As such, the current is going into the plane of the board. In that respect, the right hand must be held like this. Therefore, the direction of the current is this way. So that's nothing but it will be like this. This is the direction of the flux produced by a conductor carrying current which is moving away from the observer. On the other hand, if the current is coming towards the observer, this is the current coming towards the observer will look at the sharp end or pointer. Thus, this is the representation of the conductor. The arrow is coming out, is shown by a dot here. What will be the direction of the flux produced? You go for the hand rule, hold the thumb in the direction of the current. Current is coming out, thumb is also facing outside. Therefore, this will be the direction of the current. That is this. This will be the flux. I will stop here. I will continue with some more details in the next class. Thank you.